So today I'm going to talk about Hodge theory on Kahler manifolds. So as we will see, the theory proceeds somewhat analogously with the real case to begin with. And then at one point, we will use the Kahler condition to get some very specific information in addition to what Hodge theory would give you in case of Riemannian manifolds as detailed in a previous video. Okay, so in our setup, x omega will be a Kahler manifold, compact, and the dimension of x over C is n. Okay, so as you know, in this setup, right, so you start with H, a Hermitian metric on X with the complex structure, right? And then as you know, omega, the Kahler form, is nothing but negative twice the imaginary part of H. And then you also get a Riemannian metric that's twice the real part of H. Now, you know well that G gives an inner product on the space of K forms. Right, so this is sort of a standard construction in Riemannian geometry. And then you can, so this is a real inner product. So you can take this one step further by complexification and say that it gives a Hermitian inner product on the complexification. Right, and the way you do this, you do this the same way as how you associate to a symmetric matrix on Rn, a Hermitian matrix on C to the n, right? So simply complexifying the coefficients. Okay, good. So since in this space has some well-known subspaces, right? So the PQ forms, where P plus Q equals K, are subspaces of K forms. G naturally descends to a Hermitian inner product on these spaces as well. Okay, good. So now what you can do is you can introduce a star operator on PQ forms, which is similar to the star operator on K forms. You just have to be a bit careful with the indices. And then what this does, again, it works through a duality. So the rule for the star operator is that the inner product of UV, dVg, dVg being the Riemannian volume, is the same as U wedge star V for all UV PQ forms. Okay, as in the same way as in the Riemannian case, you see that on the right-hand side here, there's a non-degenerate pairing working, and also the left-hand side. So by composing in a sort of clever way these non-degenerate pairings, you essentially get the definition of the star, and it's uniquely determined. Now, we also know about this Delbar operator, which is in some weird way the complex analog of exterior differentiation. And then this takes PQ forms to PQ plus 1 forms. So we can think about its adjoint, right? So as we know, a formal adjoint has to exist with respect to the following inner product. So formally, this definition. And when you work things out, right? So when you look at this expression, replace it with this expression here, do exterior differentiation, and then undo things, what you will see is that actually Delbar star will equal negative star del star Delbar star star. So somehow the negative 1 power is simpler in the complex case. That is because the real dimension of complex manifolds is always even. Okay, and then also as we notice, right? So Delbar star will take PQ plus 1 forms to PQ forms. Right, and then sometimes we stick here, you know, indices PQ and here PQ plus 1 if there's a source of confusion about the indices. Okay, so you know where the story is going if you saw the previous video on Hodge theory and Riemannian manifolds. So next up, we define a notion of Laplacian. In this case, in the complex case, this is called the Hodge Laplacian. So the Hodge Laplacian is defined analogously. So it is Delbar, Delbar star, Delbar star, Delbar. And then this will take PQ forms to PQ forms. Everything is complex valued here. And then similarly, as for the same exact reason, same exact thought process, the Hodge Laplacian of a PQ form is 0 if and only if Delbar of u is 0 and Delbar star of u is 0. Okay. So no surprise, there's also a Hodge decomposition here. These are really the first hard theorems as in the real case. So what you learn is that all smooth PQ forms, space of all smooth PQ forms, decomposes in the following triple orthogonal sum. So the kernel of the Hodge Laplacian, the image of Delbar, plus the image of Delbar star, right? And then let me emphasize, I don't want to write it out. So all these sum signs here are orthogonal sums, right? So meaning that this component, when you take its orthogonal complement, it's going to be this direct sum. When you look at this component, its orthogonal complement will be this double direct sum here, etc. And there's one more thing here that we definitely want to add here. As in the real case. So you can write this again as image of Delbar star plus kernel of Delbar. In other words, these two subspaces are orthogonal to each other, and moreover, their sum gives the whole C infinity space. So showing that all these components are orthogonal to each other just takes definition of what del star is plus some integration by parts, showing that these direct sum give all elements of, so all smooth PQ forms in both cases is the hard part. And again, that's what uses elliptic PDE theory. It's something that it's worth spending time on, but again, this video is mostly a motivation. Okay, good. Okay, so this is the Hodge decomposition, and from here you get a Hodge isomorphous theorem, as in the real case. So there's a Hodge. Right. So right. So as in the real case, the kernel of the Hodge Laplacian has a name, so we will call it so these are the harmonic PQ forms. Okay. So when you put these two identities here from the Hodge decomposition, you get that the Dolbeault cohomology groups of X, which is what? The kernel of Delbar on PQ over the image of Delbar on PQ minus 1. Okay, so in this Hodge decomposition, you get that since this is an orthogonal sum here, then the kernel of Delbar has to be equal to this direct sum here. So it's kernel of Hodge Laplacian plus image of Delbar over image of Delbar. Okay, so again, since we're talking direct sum here, this is kernel of Hodge Laplacian, which is the space of harmonic PQ forms. So again, when you look at the Dolbeault cohomology groups, HPQXC, you can write that quotient as directly as a vector space, a concrete vector space of PQ forms, harmonic ones. Okay, good. Now here, so far we haven't used anything about our manifold being Kahler. So here's an important fact that I hope to show in a later video. So this is where the Kahlerness changes the game. So important fact. Okay, so the fact that X omega is Kahler implies that the Hodge Laplacian, sorry, the Laplace Beltrami is equal to 1/2 the Hodge Laplacian. So let me expand a little bit about what this really means. So as you know, Hodge Laplacian acts on PQ forms, K forms of real K forms of X, sorry, to be precise. So these are smooth sections of, it's not a bundle morphism. So as such, you can complexify it, right? And again, you complexify it simply by tensoring R tensoring C into it. So you can C there. So then these are complex valued K forms. Oops. Okay, now here PQ forms are a subspace of this, so you can just see where the P plus the Q is equal to K, right? So the complexified Laplace Beltrami acts on this space, and this gets sent in here in general. Now, in the Kahler case, what this identity means is it means that the complexified Laplace Beltrami is equal to 1/2 of the Hodge operator, Hodge Laplacian. Okay, so in particular, the image of this space also lands in the space of PQ forms because the Hodge Laplacian takes you to PQ forms, as we just learned. So in this case, tensoring with C is unnecessary. That's already part of it. Okay. So now, why is this good? Well, okay, so this implies the following, trivially implies the following fact. So obviously the kernel of the complexified Laplace Beltrami restricted to PQ forms is the same as the kernel of the Hodge Laplacian. So in other words, HK intersected with space of PQ forms is nothing but HPQ. So now, the following important consequence. So as you know, you can write the space of K forms, complexified K forms, as the direct sum of PQ forms, P plus Q equals K, so in particular, HK is equal to, trivially, HK intersected this and from all of this, it follows that you can go inside the intersection. With the intersection, you can go inside the direct sum. So you get intersected HK, and this is nothing but direct product, direct sum, P plus Q equals K, H PQ. So since each of these component here is isomorphic to HPQXC, so the corresponding Dolbeault cohomology group, and this part here, oh, sorry, here. So obviously here, you take the complexified K forms, right? So these are complex valued K forms, as we discussed in a few words in the case of Riemannian manifolds, right? So complex valued K forms are just K forms whose real and imaginary part are harmonic. So sorry, harmonic complex valued K forms are just simply complex valued K forms whose both real and imaginary part are harmonic. So I'm glad I got that out. So in particular, by the Hodge isomorphism theorem in case of Riemannian manifolds, we get this isomorphism, that this space is isomorphic to the direct sum of Dolbeault cohomology group. So deRham cohomology decomposes as Dolbeault as a direct sum of Dolbeault cohomology. So there's a couple of nice consequences of this. Let me just mention one fact, further bringing into light the usefulness of the Kahler condition. So let's suppose for a second that I am in the kernel of the Hodge Laplacian. So U is a PQ form. Now, since I know that the Hodge Laplacian is twice Laplace Beltrami, I get that the Hodge Laplacian is a real differential operator. So Hodge Laplacian is a real operator, meaning when I take the conjugate of this expression, that's going to be equivalent with Hodge Laplacian of U conjugate vanishing, right? So in particular, conjugation gives a isomorphism between HPQ and HQP, right? So we get that there is an iso between HPQ and HP, right, by simple conjugation. Okay, so this implies that these two spaces are isomorphic. Now, the analog of Betti numbers are Hodge numbers. So the dimension of Dolbeault cohomology is H small hpq. Okay, so the deRham decomposition tells us that, taking complex dimension, that the kth Betti number is the sum of the Hodge numbers PQ, where P plus Q is equal to K. Now, here's an interesting fact. So in case of K equals to 1, you get that B1 is equal to H1 0 plus H0 1. Now, due to this isomorphism between conjugates, these two are the same, right? So in particular, this is twice H1 0. So what you get from here is that for a compact Kahler manifold, B1 is always even. So if you're on a Riemannian manifold where the first Betti number is odd, then you know for sure. So, okay, so let me rephrase that. If you're on a compact Riemannian manifold where B1 is odd, then you know for sure that that structure does not admit, that manifold does not admit a Kahler structure. Now, in the same way, I'm just going to mention it. So same way, okay, there is an analog of Poincaré duality, so called Serre duality, that will essentially tell you that HPQC is isomorphic to H n minus Q n minus P x C. So in particular, the Hodge numbers HPQ and the Hodge numbers n minus Q and minus P are the same. So this also gives you some information about Betti numbers that you would not normally get in case of smooth Riemannian manifolds that are compact. Yeah, I think this is a good place to stop. Hopefully this was good motivation to look up Hodge theory in case of Kahler manifolds. All right.